A little while ago, GM began telling the customers of their Chevrolet Bolt not to use them. This is due to a rash of battery-related fires that have triggered 3 recalls and cost GM $1.8 billion in warranty costs. GM is looking to pass those costs onto their battery supplier, LG Energy Solution, sometimes also referred to as LG Chem, of which they are a recent spinoff. LG has acknowledged their responsibility in the whole situation, attributing it to a cell manufacturing quality problem. Lawsuits are probably forthcoming. This kerfuffle illustrates a going concern with this latest generation of high-energy EV batteries, fires. In this video, we're going to take a look at these high-profile electric vehicle events and what it means for the industry. For this video, I want to give my sincere thanks and appreciation to an anonymous viewer and good friend of the channel for his thoughts and technical guidance. EV batteries are a complicated thing, and I would hate to be spouting whatever. Any errors are my own, of course. Okay, first, let me talk about the Asianometry newsletter. If you subscribe to the channel, you should also sign up to the newsletter. Read the full scripts to older videos with extra commentary after the fact. There's also newsletter exclusives, like a recent one on the Maldives. You can find the link to the newsletter in the video description below, or you can just go to asianometry.com. As of right now, you can expect a new newsletter every Thursday at 1 a.m. Taiwan time. Alright, back to the show. The 2017 Chevy Bolt, made by GM, has a 60 kilowatt-hour, 350-volt lithium-ion battery pack. The 2020 version had an improved version with 66 kilowatt-hours. The pack is made of 288 lithium-ion cells in 96 modules, 3 cells in parallel, and has an expected range of about 200 highway miles. These are pouch-type cells. Their major chemistry is made up of lithium nickel oxide, lithium cobalt oxide, and lithium magnesium oxide. This nickel-rich architecture allows the car to go further and accounts for a fifth of the car's total cost. The first recall was issued in 2018. In November 2020, the company issued a software update that attempted to address the issue. But a few more fires occurred, with one of the bolts having the updated software. This led to a second recall in July 2021, and now this latest one a month later. This August 2021 recall is the most expansive thus far. It covers Chevy Bolts from the 2020 to the 2022 model years, as well as a few 2019 models that had not been covered in previous recalls. It basically recalls each one of the 141,000 Bolts ever sold. GM has advised that owners of the Bolt do the following things: park 50 feet away from other cars, park on the top floor of parking garages, monitor your car while charging, only charge the battery to 90%, do not discharge to less than 70 miles, and always park the vehicle outside. The Chevy Bolt recalls are a bitter pill for GM to swallow, considering that Bloomberg reported back in 2016 that the company was expected to take an $8,000 to $9,000 loss for each vehicle sold. Regardless, GM will replace the batteries, working with LG to scale up production of replacement battery modules. The two companies are so intimately tied together now that they have no choice but to work together through this. Divorce is not an option. When an EV battery in a car catches fire, it tends to get into the news, especially if that car happens to be a Tesla, which always gets clicks. This is for 2 reasons. The first is that EV battery fires are rare. If stored and operated within manufacturer recommended limits, a lithium-ion battery has a failure rate of 1 in 40 million. Elon Musk makes a good point that fires are a whole lot more common in internal combustion cars. EV battery fires tend to make the news because they are relatively rare. Exact comparable statistics are hard to come by, but in 2019, there were 190,000 conventional vehicle fires in the United States, as his Dogeness points out. Of course, this stat is in part due to the fact that electric vehicles themselves make up a relative minority of the overall car population. But there is some automobile insurance data that shows that EVs tend to have a lower rate of vehicle fires. And of course, it is also necessary to counterpoint that EV owners tend to be wealthier and thus possibly are better or more careful drivers, thus the lower car fire rate. As Twain says, there are lies, damned lies, in statistics, such and such. The second big reason these EV fires tend to make the news, however, is indeed very safety related. It is because, like I hinted at earlier, these fires tend to burn big and hot. To know why that is the case, we need to look inside the battery itself. If you recall, batteries always have a number of common components: the anode, the cathode, electrolyte, and separator. During normal operations, lithium ions move from the anode to the cathode, and this drives the machine. In recent years, customers have come to expect more from their electronics. For instance, more range and faster charging times for their EVs. To meet this demand, the market has developed and introduced new chemistries, especially in the cathode space. These include nickel-rich and manganese-rich materials, and a bunch of other stuff that sounds like it belongs in a hard sci-fi novel. Vanadium pentoxide, or carbon-coated lithium iron phosphate nanospheres. Manufacturers walk a balancing rope. Adding more of these materials can increase how long the battery can discharge energy, or how much energy it can discharge. But doing that can also lead to thermal instability and really bad fires. If the battery gets too hot, is damaged for whatever reason, or has manufacturer flaws, then there are fire risks. It can lead to what is euphemistically referred to within the industry as thermal runway. Batteries catch on fire for any number of reasons. For this specific scenario, I would discuss a temperature-induced one. When things are operating normally, the battery cells generate heat, but that heat is relatively low and safely dissipates out of the module. The battery's internal structure remains sound. But as the temperature rises and keeps rising beyond certain thresholds, then the battery's components start to transform, chemically. And if there is nothing to stop this, then it can lead to thermal runway. The first thing to go would be the solid electrolyte interface layer, or the SEI. The SEI layer is formed on the anode as part of the electrochemistry manufacturing process. This impermeable layer protects the anode from reacting with the electrolyte's molecules. I mentioned this in my video about EV battery manufacturing. You can learn more about the whole process in that one. Anyway, when the temperature gets too high, usually at around the 90 to 120 degrees Celsius level, the SEI breaks down. This generates additional heat and creates carbon dioxide in the process. The chain reaction can now continue. With the SEI layer gone, the barbarians of the electrolyte can breach the gates and react with the anode. This generates yet more heat, as electrolyte reactions tend to be especially hot. With the temperature at over 135 degrees Celsius, the separator loses its structural integrity. The separator is an important safety measure inside the battery. With the separator no longer separating, the anode and the cathode come into contact and causes what is called an internal short circuit. An internal short circuit is the single most common reason why an EV battery starts to catch fire. At this point, the battery begins to self-discharge. The cathode and anode start to decompose, releasing oxygen and yet more heat. Different chemistries of cathodes are more vulnerable to this decomposition than others. Lithium cobalt oxides probably most so, lithium iron phosphates probably least vulnerable and thus tend to be the most safe, but with different drawbacks of their own. When the temperature gets over 200 degrees Celsius, the electrolyte also decomposes, releasing its own heat. Critically, the decomposition releases reactive and potentially explosive gases like carbon dioxide, hydrocarbons, and fluoride gases. By now, every part of the whole battery is breaking down and the car is likely on fire, a fire exceptionally difficult to put out. EV fires are not your regular garden variety car fires, if such a thing exists. Because they are partially caused by direct reactions between battery components, they may not require external oxygen. Therefore, firefighters generally find them more difficult to extinguish than conventional vehicle fires. One example in the city of Fort Lauderdale in the United States took between 750 to 1,100 liters of water. In some cases, it can take over 10,000 liters of water and over 60 minutes to suppress an EV fire. This is substantially more than the 5 minutes for a conventional car fire. Firefighters tend to use water to smother a fire, but this may lead to additional risks. The salt in the electrolyte, briskly named lithium hexafluorophosphate, can react with the water to create hydrogen fluoride, a corrosive gas. Hydrogen fluoride is used in the petrochemical industry to create superacids. Enough said. And water being poured into the battery can cause additional short circuits. It is known that dirty water leaching into the battery's innards can spark EV fires. There have been a few EV bus incidents in China of such. Furthermore, EV batteries have a tendency to reignite long after the fire has been seemingly extinguished. This is due to residual energy inside the battery. For instance, the battery in the Fort Lauderdale car fire reignited as the burnt vehicle was being towed away from the crash scene. That fire was quickly put out, but then it lit up again once it arrived at the salvage yard. Another EV fire in South Jordan, USA also reignited the same day of the crash and then again 5 days thereafter. Considering that an EV battery fire is not your ordinary fire, manufacturers have gone to great measures to install systems to prevent them from happening. There are a variety of reasons why battery fires can start. Sometimes they never find the reason. Thus, manufacturers have engineered a variety of safety measures to either prevent thermal runaway from ever starting or from getting out of control. Some measures are no-brainers, others require balancing trade-offs. For instance, enlarging the space between the cells in the modules. Tests in the lab find that if one cell is compromised, it can heat up its neighbors and cause chain reactions. For this reason, sometimes manufacturers add literal firewalls between the cells. But doing something like this reduces energy density and cuts down on the vehicle's range. Customers might be less willing to buy such a car. So, trade-offs. The battery management systems within the modules are also critical. Separating a module and its cell's electrical systems can prevent a total thermal runaway event. And since modules are the pack's nervous system, software can be incorporated to predict a cell's possibility of thermal runaway based on charge levels and temperature changes. The latter, since abrupt variations of heat are just as dangerous as the absolute level of heat. For the cells themselves, manufacturers have identified the separator as a critical safety measure to prevent thermal runaway. The reason why the separator is mostly made of polymer is that when it gets too hot, the pores in the polymer close, a process called separator shutdown. This keeps the cathodes and anodes from meeting and prevents an internal short circuit from happening. Reactions will stop, and, so long as the separator maintains its structural integrity, the battery can start to calm down. Engineers have implemented triple-layer separators and ceramic-coated polymer hybrids that maintain their stability even throughout difficult temperatures. It is important to remember, however, that every item has its limit. And to deal with thermal runaway gases from causing potential explosions, cells can be made with fail-safe venting mechanisms. There are a variety of granted patents for them. Cylindrical 18650 batteries can have small vent windows, pressure-sensitive caps, or simple sealed pinholes. This is by no means a comprehensive review of EV battery safety mechanisms. I have literally just scratched the surface. But it gives you a window into just how big of a deal it is in the minds of manufacturers. And despite all of that, things can still go wrong. There is no doubt that this recall is a hit to LG Energy. The company prides itself on its advanced chemistries and industry-standard pouch designs for its battery cells. Whether or not there might be something actually fundamentally wrong with LG's pouch design, as Elon seems to imply in a tweet, that's harder to say. The issue that is more interesting to consider is whether actual or perceived safety risks with these nickel-rich battery chemistries are going to have car makers opting for lithium iron phosphate batteries. As I briefly mentioned, these chemistries tend to be safer when it comes to thermal runaway, but they do have drawbacks in the form of energy density and weight. Companies like BYD and CATL dominate the lithium iron phosphate world in terms of production and patents. They're doing some really interesting things with cell-to-pack that attempt to ameliorate those aforementioned drawbacks. Tesla using lithium iron phosphate in some of their Chinese Model 3s might be an indication that these chemistries are getting good enough. It is likely that the Chinese players gain share in areas like Norway, where range is less of a concern. As for the industry as a greater whole, EV momentum is too strong right now. GM has committed to putting out a whole series of electric cars in the future. Companies like Ford and Porsche are making electric versions of their flagship cars. A few bumps along the road is a willing price to bear for a greener future. That being said, never overcharge your EVs, folks. Alright everyone, that's it for tonight. Thanks for watching. If you enjoyed the video, consider subscribing. Check out the newsletter or follow the Twitter. Want to send me an email? Drop me a line at john@asianometry.com. I love reading your emails. Introduce yourself, suggest a topic, or more. Until next time, I'll see you guys later.